Hey everyone! Tonight, we're venturing into the cosmic cradles where stars are born. Before we begin this gentle exploration, take a moment to like this if these deep space journeys resonate with you, and share in the comments where you're listening from and what time it is in your corner of the world. I'm always moved by how our global community comes together to contemplate the infinite cosmos. Now, settle in comfortably, let those lights fade to darkness. Tonight, we're not seeking explosive cosmic drama or alien civilizations. Instead, we're going to witness something far more profound and peaceful: the patient, inevitable birth of stars from the seemingly empty darkness of space. Let's embark on our meditative journey into the infinite. In the vast stretches between the stars, where space appears utterly empty to our eyes, magnificent cosmic nurseries drift silently through the galaxy. These are the molecular clouds, immense cathedrals of gas and dust, each one spanning hundreds of light years, each one a fertile realm, where gravity works its ancient magic over millions of years. Tonight, we'll explore these stellar nurseries, witnessing the delicate dance between cosmic forces that transforms cold, dark matter into blazing suns. We'll discover how these seemingly tranquil clouds harbor invisible dramas of physics, where gravity and gas pressure engage in eternal balance, where magnetic fields thread through space like cosmic spider webs, and where the gentlest disturbances can trigger cascades of stellar birth that echo across geological time. We'll journey from the largest scales, clouds that could swallow entire solar systems, down to the intimate moments when a protostar first begins to glow with the promise of nuclear fire. This is a story of patience and inevitability, of cosmic processes that unfold over timescales that dwarf human civilization, yet connect intimately to our own origins. Every atom in your body was once part of such a cloud, waiting in the darkness for gravity's call to begin the journey toward becoming part of a star, a planet, and ultimately, you. In the vast cathedral of space, where darkness stretches between the familiar points of starlight, there exist regions of profound cosmic significance that remain largely invisible to our eyes. These are the molecular clouds, the stellar nurseries where the universe quietly orchestrates its most fundamental creative process, the birth of stars. Within these seemingly empty expanses of space, spanning hundreds of light years, in their grandest manifestations lies the raw material from which all stellar light emerges. These cosmic cradles drift through our galaxy with a patience that transcends human comprehension, their movements measured not in days or years, but in the slow procession of millions of years. Each molecular cloud represents a repository of primordial material, gas and dust that has wandered through space since the early epochs of our galaxy's formation. The hydrogen molecules that comprise the bulk of these clouds carry within them the memory of cosmic evolution, having formed in the cold depths of space where temperatures hover just above absolute zero. The architecture of these stellar nurseries reveals itself as a masterpiece of cosmic engineering. Picture, if you will, a structure so vast that light itself requires centuries to traverse its breadth, yet so tenuous that the entire mass of material contained within would create a vacuum far more complete than any achievable in terrestrial laboratories. The density of matter in these clouds is so extraordinarily low that a volume the size of Earth's atmosphere would contain only a few handfuls of atoms scattered like cosmic dust motes in an infinite ballroom. Within this apparent emptiness, however, lies a complexity that rivals the most intricate terrestrial ecosystems. The molecular clouds are not uniform expanses of gas, but rather exhibit a delicate filamentary structure with tendrils of material threading through space like the neural networks of some cosmic mind. These filaments, invisible to optical telescopes but revealed through radio observations, create a three-dimensional web of matter that serves as the scaffolding upon which future stars will be constructed. The temperature within these stellar nurseries maintains a profound chill, typically hovering around 10 degrees above absolute zero. This extreme cold is not merely an absence of heat, but represents a fundamental condition that allows the complex chemistry of star formation to proceed. At these temperatures, hydrogen atoms combine to form molecules, and these molecules can then condense onto microscopic dust grains that float through the cloud like cosmic snowflakes, each one potentially serving as a nucleus around which stellar material might eventually gather. The dust grains themselves tell a story of cosmic recycling that spans billions of years. These tiny particles, typically smaller than the wavelength of visible light, are composed of materials forged in the nuclear furnaces of previous generations of stars. Silicon, carbon, oxygen, and iron atoms expelled from dying stars in their final moments have condensed into these microscopic seeds that now drift through the molecular clouds, waiting to participate in the birth of new stellar systems. Magnetic fields thread through these cosmic nurseries like invisible rivers, their presence detectable only through their subtle influence on the polarization of light from background stars. These magnetic field lines, stretched and twisted by the slow motions of the gas, provide a form of structural support that helps maintain the cloud's integrity against the inexorable pull of its own gravity. The interplay between magnetic forces and gravitational attraction creates a delicate balance that can persist for millions of years, allowing the cloud to exist in a state of suspended animation, neither collapsing nor dispersing. The Orion Molecular Cloud Complex, perhaps the most studied stellar nursery in our cosmic neighborhood, exemplifies the grandeur of these cosmic structures. Located approximately 1,500 light-years from Earth, this vast region of space contains enough material to form thousands of stars, like our Sun. Within its boundaries, astronomers have identified numerous sites where star formation is actively occurring, each representing a different stage in the complex process of stellar birth. In the vast cathedral spaces between the stars, where darkness stretches across distances that dwarf human comprehension, there exists a delicate cosmic ballet of invisible forces locked in eternal embrace. Within the molecular clouds that drift like silent leviathans through the galaxy, gravity and gas pressure engage in a dance so subtle, so perfectly balanced, that it has persisted for millions upon millions of years, waiting for the precise moment when equilibrium yields to the inexorable pull of stellar birth. The balance that maintains these cosmic nurseries in their peaceful state is governed by principles that James Jeans first glimpsed in the early years of the 20th century. In 1902, this brilliant physicist recognized that within every cloud of gas and dust, there exists a critical threshold, a precise mass beyond which gravity's patient accumulation of matter will overwhelm the gentle outward pressure of the gas itself. This threshold, now known as the Jeans mass, represents one of the universe's most fundamental boundaries, the invisible line between cosmic stability and the inevitable collapse that births new stars. Consider the mathematics of this cosmic equilibrium, expressed in equations that capture the essence of forces operating on scales almost beyond imagination. The gravitational potential energy of a cloud, slowly drawing particles together across light years of space, must be balanced against the thermal kinetic energy of gas molecules moving at temperatures just above absolute zero. When we peer into these calculations, we discover that a typical molecular cloud, with its gossamer density of perhaps a few hundred particles per cubic centimeter, can maintain its structural integrity for timescales that span the rise and fall of entire civilizations on distant worlds. The temperature within these stellar nurseries hovers at a mere 10 to 20 degrees above absolute zero, creating conditions so cold that molecules move with the languid grace of cosmic ballet dancers. At these frigid temperatures, the thermal pressure, the collective push of countless molecular motions, provides just enough resistance to counteract gravity's gentle but persistent pull. This balance is so precise that astronomers have observed molecular clouds maintaining their basic structure for periods exceeding 10 million years, drifting through space like sleeping giants, their internal architecture preserved by the perfect equilibrium of opposing forces. Yet this balance extends far beyond the simple interplay of gravity and thermal pressure. Threading through these cosmic clouds like invisible scaffolding, magnetic fields contribute their own subtle influence to the maintenance of equilibrium. These magnetic field lines, stretched and twisted by the slow churning motions within the cloud, provide additional support against gravitational collapse. The magnetic pressure arising from the tendency of field lines to resist compression adds another layer of complexity to the delicate balance that keeps these stellar nurseries in their dormant state. Turbulence, too, plays its role in this cosmic equilibrium. The molecular clouds are not static entities, but rather dynamic systems filled with gentle, chaotic motions on scales ranging from the microscopic to the truly astronomical. These turbulent eddies, cascading from large-scale flows down to the smallest resolvable structures, create an additional source of pressure that helps support the cloud against its own gravitational attraction. The energy dissipated by this turbulence is gradually replenished by various mechanisms, including the stirring effects of stellar winds from nearby stars and the slow shearing motions induced by the galaxy's rotation. When we examine specific examples of this cosmic balance in action, we find molecular clouds like Barnard 68, a nearly perfect sphere of darkness silhouetted against the background stars. This remarkable object, located approximately 500 light-years from Earth, represents a textbook example of a cloud in near-perfect hydrostatic equilibrium. Its spherical symmetry suggests that internal pressures are balanced in all directions, creating a stable configuration that has persisted for countless millennia. The cloud's edges are so sharply defined that they appear almost artificial, as if drawn by some cosmic architect with a perfect compass. The Orion Molecular Cloud Complex provides another magnificent example of forces in equilibrium, though on a far grander scale. This vast stellar nursery, spanning hundreds of light years and containing enough material to form thousands of stars like our Sun, demonstrates how equilibrium can be maintained even in systems of enormous complexity. Different regions within the cloud exhibit varying degrees of stability, with some areas remaining quiescent, while others show signs of incipient collapse. This patchwork of stability and instability reveals the subtle variations in local conditions that determine whether a particular region will remain dormant or begin its transformation into a stellar birthplace. The mathematical framework that describes this equilibrium, the virial theorem, reveals the profound simplicity underlying these complex systems. This theorem states that for a gravitationally bound system in equilibrium, the kinetic energy of internal motions must equal exactly half the magnitude of the gravitational potential energy. This relationship, first derived in the context of statistical mechanics, finds its most beautiful expression in the realm of stellar nurseries, where it governs the long-term stability of structures containing masses equivalent to thousands of suns. As we contemplate these vast scales of cosmic equilibrium, we begin to appreciate the patience of the universe in its creative processes. The molecular clouds drift through space for millions of years, their internal forces locked in perfect balance, waiting for the moment when some external influence will tip the scales toward gravitational collapse. This waiting period, measured in units that dwarf human history, represents a kind of cosmic meditation, a state of suspended animation in which the potential for stellar birth lies dormant, gathering strength for the moment of awakening that will transform cold, dark matter into the blazing furnaces that light the galaxy. In the vast cathedral of space, where molecular clouds drift in their ancient silence, there exists a profound tension between stability and change. These cosmic structures, having maintained their delicate equilibrium for millions of years, occasionally encounter forces that disturb their peaceful existence. Like a still pond suddenly touched by a gentle breeze, these disturbances ripple through the cloud's fabric, awakening processes that have slumbered since the cloud's formation. The most dramatic of these cosmic disturbances arrives in the form of shockwaves, invisible tsunamis of energy that race through the interstellar medium at speeds that dwarf our earthly comprehension. When a massive star reaches the end of its life and explodes as a supernova, it releases energy equivalent to our sun's entire lifetime output in mere seconds. This titanic explosion sends shockwaves radiating outward like ripples on a cosmic pond, traveling at thousands of kilometers per second through the thin medium of space. These shockwaves carry with them the memory of stellar death, compressing and heating the gas they encounter. When such a wave encounters a molecular cloud, it acts like a cosmic sculptor's chisel, compressing the cloud's leading edge and triggering instabilities that can propagate throughout the entire structure. The compression increases the cloud's density, tipping the delicate balance between gravity and pressure that has maintained the cloud's stability for eons. Consider the ancient explosion that created the Orion-Eridanus superbubble, a vast cavity in space carved by multiple supernovae over the past 10 million years. This cosmic excavation has swept up surrounding material, creating a shell of compressed gas that continues to influence star formation in the region. The shock waves from these long-ago explosions still reverberate through nearby molecular clouds, their effects visible in the active star formation occurring in the Orion Nebula Complex today. Stellar winds provide another source of gentle but persistent disturbance. Massive stars, burning through their nuclear fuel at prodigious rates, drive powerful winds of charged particles into space. These winds, though more subtle than supernova shock waves, can inflate enormous bubbles in the surrounding medium over millions of years. The hot, tenuous gas within these bubbles exerts pressure on nearby molecular clouds, slowly but inexorably compressing their outer layers. The Wolf-Rayet stars, among the most massive and luminous stars in the galaxy, exemplify this process. These stellar giants lose mass at rates thousands of times greater than our Sun, creating cavities dozens of light years across. The boundaries of these wind-blown bubbles become sites of enhanced star formation as the compressed gas reaches critical densities for gravitational collapse. Sometimes, the universe orchestrates more subtle disturbances through the gravitational dance of celestial mechanics. As molecular clouds orbit the galactic center, they occasionally encounter massive stars or stellar associations whose gravitational fields can trigger instabilities within the cloud structure. These gravitational perturbations act like cosmic tuning forks, setting up resonances that can fragment the cloud into smaller, denser regions. The spiral arms of our galaxy create their own unique form of disturbance through what astronomers call spiral density waves. These are not physical structures, but rather regions of enhanced gravitational attraction that sweep around the galaxy like cosmic traffic jams. As molecular clouds enter these spiral arms, they experience compression from the increased gravitational field, often triggering episodes of star formation that illuminate the spiral structure with chains of bright, young stars. Perhaps most remarkably, molecular clouds can disturb themselves through their own internal dynamics. Turbulence within the cloud, driven by magnetic field interactions and thermal instabilities, creates a constantly shifting pattern of density fluctuations. These internal motions, though chaotic in detail, follow statistical patterns that astronomers are only beginning to understand. The turbulence acts like a cosmic stirring mechanism, occasionally creating regions of enhanced density that become seeds for future star formation. Cloud-cloud collisions represent another pathway to disturbance, though these cosmic encounters unfold over timescales that stretch human imagination. When two molecular clouds meet in the depths of space, their collision occurs at speeds measured in kilometers per second, fast by terrestrial standards, but glacially slow compared to the shock waves from stellar explosions. The collision compresses gas at the interface between the clouds, creating conditions favorable for gravitational collapse. The antennae galaxies, locked in their billion-year embrace, provide a spectacular example of how galactic collisions can trigger widespread cloud disturbances. The gravitational interaction between these merging galaxies has compressed molecular clouds throughout both systems, igniting starbursts that illuminate the collision with the brilliant light of newborn stars. These various disturbances share a common thread. They all serve to compress the molecular cloud material, increasing its density and bringing it closer to the critical threshold where gravity can overcome the outward pressure of the gas. The process is remarkably patient, often requiring hundreds of thousands of years for the disturbance to propagate through the cloud and trigger the first signs of collapse. In this cosmic symphony of disturbance and response, we witness the universe's remarkable ability to create order from chaos, to birth new stars from the gentle violence of shock waves and gravitational encounters. Each disturbance carries within it the seeds of future stellar generations, ensuring that the cycle of cosmic creation continues across the vast expanses of space and time. In the vast cathedral of space, where molecular clouds drift like cosmic leviathans through the darkness, there comes a moment when the delicate balance that has maintained their peaceful existence for millions of years begins to shift. This is the moment when gravity, that most patient and persistent of cosmic forces, finally claims its inevitable victory over the gentle resistance of gas pressure and magnetic support. The collapse of a molecular cloud is not the dramatic, explosive event that our human minds might imagine. Instead, it unfolds with the slow majesty of geological time, a process so gradual that entire civilizations could rise and fall, while a single cloud fragment contracts toward its stellar destiny. Yet within this apparent stillness lies one of the universe's most profound transformations, the inexorable surrender of diffuse matter to the fundamental force that shapes all cosmic architecture. When the critical threshold is crossed, when the John's mass criterion tips the scales in favor of gravitational attraction, the cloud begins its freefall collapse with a time scale that speaks to the immense distances involved. For a region destined to become a star like our Sun, this collapse phase spans approximately 100,000 years, a duration that encompasses the entire span of modern human civilization. The mathematics of this process, first worked out by astronomers in the early 20th century, reveal the elegant simplicity underlying cosmic complexity. As the cloud contracts under its own gravitational pull, it begins to fragment in a beautiful hierarchical cascade, like a cosmic Russian nesting doll, revealing smaller and smaller structures within. This fragmentation occurs because different regions of the cloud have slightly different densities and temperatures, creating a natural tendency for the material to break apart into discrete clumps. Each fragment becomes a potential stellar nursery, a concentrated region where the conditions for star formation become increasingly favorable. The process of fragmentation continues on multiple scales, from the original cloud spanning hundreds of light years down to dense cores only a few thousand times the distance between Earth and Sun. Within these cores, the temperature remains extraordinarily cold, just 10 to 20 degrees above absolute zero, while the density slowly increases from the tenuous conditions of interstellar space toward the compressed states found in stellar interiors. Conservation of angular momentum plays a crucial role in shaping the collapse, as any initial rotation in the cloud becomes amplified as the material contracts. Like a figure skater pulling in their arms, the slowly spinning cloud begins to rotate faster as it shrinks, eventually forming the flattened, disc-like structures that will become the birthplaces of planetary systems. This rotation also helps to regulate the collapse, preventing the material from falling directly into the center and instead creating the complex accretion flows that characterize protostellar formation. The formation of the first hydrostatic core marks a pivotal moment in stellar evolution, when the collapsing material becomes dense enough that it can no longer radiate away the heat generated by compression. This core, roughly the size of our solar system, but containing only a small fraction of the final stellar mass, represents the first stable structure to emerge from the chaos of gravitational collapse. It glows with a faint infrared light, powered not by nuclear fusion, but by the gentle release of gravitational potential energy. Modern computer simulations have revealed the intricate beauty of this collapse process, showing how turbulent motions within the cloud create complex flows and eddies that influence the final properties of the forming star. These simulations, running on the most powerful supercomputers available, must track the evolution of matter across more than 10 orders of magnitude in density, from the initial cloud conditions to the formation of the protostellar core. The collapse is not uniform, but proceeds in waves, with different regions of the cloud reaching critical density at different times. This creates a complex temporal symphony of star formation, where the birth of one generation of stars can trigger the formation of the next through shock waves and radiation pressure. The process demonstrates the interconnected nature of cosmic evolution, where individual stellar births are part of a larger choreography spanning galactic scales. As we contemplate this slow-motion avalanche of cosmic material, we witness gravity's patient artistry in sculpting the universe's most fundamental building blocks. The collapse of molecular clouds represents one of nature's most elegant solutions to the challenge of concentrating diffuse matter into the dense, hot conditions required for nuclear fusion. In this gradual surrender to gravitational inevitability, we see the universe's remarkable ability to create order from apparent chaos, transforming the cold, dark expanses between stars into the brilliant beacons that illuminate the cosmic night. In the depths of space, where darkness reigns supreme and silence stretches across unimaginable distances, a profound transformation begins to unfold. The protostellar core, now dense and warm from the gentle embrace of gravitational collapse, enters a phase of cosmic awakening that will span hundreds of thousands of years. This is the delicate dance between matter and energy, between the ancient cold of space and the emerging warmth of stellar birth. The protostar, still deeply embedded within its cocoon of dust and gas, begins to gather material from its surroundings with the patience of cosmic time itself. Like a slowly spinning whirlpool in the vastness of space, matter spirals inward, each particle carrying with it the angular momentum inherited from the original molecular cloud. This accretion process unfolds with the measured rhythm of celestial mechanics, each grain of dust and molecule of gas adding its infinitesimal contribution to the growing stellar embryo. As material continues to fall toward the central protostar, something magnificent begins to take shape in the surrounding space. The conservation of angular momentum, that fundamental law of physics that governs the motion of all things in the universe, ensures that the infalling material cannot simply plunge directly into the protostar. Instead, it forms a circumstellar disk, a cosmic record player of gas and dust that extends outward for hundreds of astronomical units. This disk, glowing faintly with the heat of friction and gravitational energy, represents the birthplace of future planetary systems. The disk itself is a marvel of cosmic architecture, its structure determined by the delicate interplay of gravity, pressure, and magnetic fields. In the inner regions, where temperatures soar to hundreds of degrees above absolute zero, rocky materials begin to condense from the primordial vapor. Further out, where the cold of space still dominates, water ice and other frozen compounds accumulate on the surfaces of dust grains. This temperature gradient, established by the young protostar's feeble luminosity, will eventually determine the architecture of any planetary system that might form. Within this disk, turbulence creates eddies and streams of material, mixing and redistributing the elements that were forged in the cores of previous generations of stars. The iron that will one day flow in the veins of living beings, the silicon that will form the rocky foundations of terrestrial worlds, the carbon that will become the backbone of organic chemistry. All these elements swirl together in the cosmic dance of accretion. The protostar itself grows slowly but inexorably, its mass increasing as material from the disk spirals inward. This accretion process releases tremendous amounts of gravitational potential energy, causing the protostar to glow with a luminosity that can exceed that of our present-day sun. Yet this light remains hidden from direct view, absorbed by the dense envelope of dust and gas that still surrounds the forming star. Only in the infrared portion of the electromagnetic spectrum can we glimpse the warm glow of this cosmic chrysalis. As the protostar continues to evolve, remarkable phenomena begin to manifest along its rotation axis. Powerful magnetic fields generated by the motion of charged particles within the accreting material channel some of the infalling gas into narrow jets that stream away from the protostar at velocities of hundreds of kilometers per second. These bipolar outflows, invisible to the naked eye, but detectable through radio and infrared observations, carve cavities in the surrounding molecular cloud, creating the first clear windows through which the young star might eventually be seen. The formation of these jets represents one of nature's most elegant solutions to the problem of angular momentum transport. As material spirals inward through the disk, it must somehow lose its angular momentum to continue its journey toward the central star. The magnetic fields threading through the disk act as cosmic brakes, transferring angular momentum outward while allowing mass to flow inward. Some of this angular momentum is carried away by the jets themselves, launched from the innermost regions of the disk where magnetic forces are strongest. Over time, as the protostar continues to accrete material and grow in mass, its internal structure begins to change. The central regions, compressed by the weight of overlying material, gradually heat up as gravitational potential energy is converted to thermal energy. When the core temperature reaches about 10 million degrees Celsius, a threshold is crossed that will forever change the nature of the object. Nuclear fusion begins, as hydrogen nuclei overcome their mutual electrical repulsion and fuse together to form helium, releasing energy in the process. This moment marks the true birth of a star, the transition from a gravitationally contracting object to a self-sustaining nuclear furnace. The energy released by fusion creates an outward pressure that balances the inward pull of gravity, establishing the hydrostatic equilibrium that will characterize the star's main sequence lifetime. The protostar has become a star, joining the ranks of the hundreds of billions of stellar beacons that illuminate our galaxy. Yet even as nuclear fusion begins in the core, the young star retains many characteristics of its protostellar youth. The surrounding disk continues to feed material onto the stellar surface, causing periodic outbursts of brightness as clumps of matter spiral inward and are accreted. The stellar surface itself remains active and variable, covered with dark spots and bright flares as the star's magnetic field interacts with the surrounding material. This phase of stellar evolution, known as the T-Tauri phase after the prototype star discovered in the constellation Taurus, can last for several million years. During this time, the young star gradually clears away the remaining material from its birth environment, its stellar winds and radiation pressure slowly dispersing the dust and gas that once shrouded it from view. The circumstellar disk, meanwhile, begins its own evolution as dust grains stick together to form ever larger aggregates that will eventually become the building blocks of planets. In the vast cosmic theater where stars are born, we encounter not isolated events, but entire communities of stellar creation, ecosystems of birth and growth that span hundreds of light years and millions of years. These stellar nurseries function as cosmic cities, where the birth of one star influences countless others, creating intricate webs of interaction that shape the very fabric of our galaxy. Within these nurseries, we find stellar associations and open clusters, loose congregations of stars that share common origins in the same molecular cloud. Like siblings born from the same cosmic womb, these stars begin their lives together, their fates intertwined by the circumstances of their birth. The most massive among them, blazing blue giants that burn through their nuclear fuel with fierce intensity, become the architects of their stellar neighborhoods, their powerful winds and intense radiation carving cavities in the surrounding gas and dust. Consider the magnificent Orion trapezium cluster, where 4 massive stars dominate the central region of the Orion Nebula. These stellar titans, each dozens of times more massive than our Sun, pour forth torrents of ultraviolet radiation that ionize the surrounding gas, creating the glowing beauty we observe. Their stellar winds, racing outward at thousands of kilometers per second, sweep away the natal material, gradually clearing the nursery of its birth cocoon. This process of stellar feedback creates a complex dance between destruction and creation, as the energy from these massive stars both disperses the remaining gas and triggers new waves of star formation in the compressed material at the edges of the expanding bubble. The initial mass function, a fundamental relationship discovered through decades of careful observation, reveals that nature produces far more low-mass stars than high-mass ones. For every massive star that blazes brilliantly for a few million years, hundreds of smaller, longer-lived stars are born. This cosmic preference for modesty ensures that the galaxy's stellar population remains stable over billions of years, with the majority of stars burning steadily for timescales that dwarf the age of complex life on Earth. As we observe these stellar nurseries across different wavelengths of light, we witness the sequential patterns of star formation that unfold like slow-motion fireworks across cosmic time. The birth of massive stars creates expanding shells of compressed gas that, in turn, trigger the formation of new stellar generations. This process, known as sequential star formation, creates age gradients across star-forming regions, with the oldest stars found in the centers of cleared cavities and the youngest embedded in the compressed material at the periphery. The Carina Nebula exemplifies this multi-generational stellar community, where several episodes of star formation have occurred over the past 10 million years. The massive stars of earlier generations have carved out vast cavities in the molecular cloud, while their stellar winds continue to compress the surrounding material, triggering new rounds of stellar birth. Within this cosmic nursery, we observe stars in every stage of development, from deeply embedded protostars still gathering mass to fully formed main sequence stars that have cleared their surroundings and begun their long stellar lives. Environmental factors play crucial roles in determining the properties of newly formed stars. Stars born in the dense cores of massive molecular clouds experience different conditions than those forming in the sparse outer regions. The presence of nearby massive stars can truncate the formation process, creating lower mass stars than would otherwise form, while the metallicity of the parent cloud influences the efficiency of cooling and fragmentation, affecting the entire stellar population. The gradual dispersal of stellar nurseries marks the end of active star formation in any given region. As massive stars evolve and explode as supernovae, their energy input becomes so intense that the remaining gas is expelled entirely, leaving behind only the stellar population and any planetary systems that may have formed. Open clusters like the Pleiades represent this later stage, where the stars have emerged from their dusty cocoons and begun their independent journeys through the galaxy, slowly drifting apart under the influence of galactic tides and gravitational perturbations. These stellar communities serve as laboratories for understanding fundamental astrophysical processes, their proximity allowing us to study stellar formation and evolution in exquisite detail. Through patient observation and careful analysis, we trace the connections between stellar birth environments and the properties of the resulting stellar populations, building our understanding of how stars shape their cosmic neighborhoods and, ultimately, how they contribute to the chemical and dynamical evolution of entire galaxies. In the vast theater of cosmic discovery, humanity has developed increasingly sophisticated eyes to peer into the hidden realms of stellar birth, each technological advance revealing new layers of wonder in the seemingly empty spaces between stars. The story of observing stellar nurseries unfolds like a gentle awakening of our cosmic consciousness, beginning with the earliest glimpses of nebulous patches of light that puzzled astronomers for centuries, and evolving into today's magnificent ability to witness the very moment when gravity triumphs over gas pressure in the birth of new worlds. The journey of revelation began with simple optical telescopes, those first windows into the cosmic deep that revealed mysterious clouds of light scattered across the night sky. William Herschel, in his patient sweeps of the heavens during the late 18th century, catalogued these nebulous objects with the methodical devotion of a cosmic botanist, not knowing that he was documenting the universe's most fertile regions. These early observers could only see the illuminated edges of vast molecular clouds, the regions where newly born stars had begun to shine their light into the surrounding darkness, creating the glowing boundaries that marked the presence of something far more vast and complex than they could imagine. The true revolution in understanding stellar nurseries came with the development of radio astronomy in the middle of the 20th century, when scientists learned to listen to the whispers of molecules drifting through space. Radio telescopes, those great metal ears turned toward the cosmos, revealed that the seemingly empty regions between stars were actually filled with a rich symphony of molecular emissions. Each molecule, hydrogen, carbon monoxide, water vapor, and hundreds of others, sang its own unique frequency, creating a cosmic orchestra that told the story of temperature, density, and motion within the clouds. The discovery that space was filled with this molecular music transformed our understanding of stellar birth from a visual phenomenon to a multisensory experience of cosmic chemistry and physics. The gentle penetration of infrared radiation through cosmic dust opened another window into the hidden processes of stellar formation, where optical light was absorbed and scattered by the tiny grains floating through molecular clouds. Infrared radiation could pass through like sunlight through morning mist, revealing the warm cores where gravitational collapse was beginning to heat the surrounding material. Space-based infrared telescopes like Spitzer and Herschel became our cosmic time machines, allowing us to see the earliest stages of stellar evolution hidden within their dusty cocoons, watching as cold cores slowly warmed and brightened over thousands of years of patient observation. The development of interferometry brought unprecedented resolution to our observations of stellar nurseries, combining the light from multiple telescopes to create virtual instruments with the resolving power of dishes spanning continents. The Atacama Large Millimeter Array, perched high in the Chilean desert where the thin, dry air provides perfect conditions for millimeter wave observations, has revolutionized our ability to see the intricate structure within molecular clouds. These observations reveal stellar nurseries as vast, complex ecosystems with filamentary structures threading through space like cosmic spider webs, dense cores embedded within the filaments like dewdrops on silk, and the earliest stages of disk formation around newly born protostars. Modern observations have revealed that stellar birth is not a simple, isolated event, but rather a complex process involving the interaction of multiple physical mechanisms across vast ranges of scale and time. High-resolution radio observations show us the turbulent motions within molecular clouds, the shock waves propagating through the gas, and the magnetic fields that thread through the material like invisible scaffolding. Infrared observations reveal the thermal structure of collapsing cores, the formation of circumstellar disks, and the powerful jets that stream away from young protostars. X-ray observations detect the high-energy processes associated with stellar youth, the magnetic reconnection events and accretion shocks that mark the violent awakening of gravitational energy in collapsing systems. The combination of these observational techniques has allowed astronomers to create detailed models of stellar birth that span the entire process from initial cloud formation to the emergence of main-sequence stars. Computer simulations, guided by observational constraints, now follow the collapse of molecular cloud cores through millions of years of evolution, tracking the formation of protostellar disks, the launching of bipolar outflows, and the gradual clearing of the natal envelope as the young star begins to shine with its own light. These models reveal stellar birth as a process of exquisite complexity and beauty where the simple force of gravity, acting over cosmic timescales, creates the intricate structures that will eventually become planetary systems and the chemical factories that enrich the universe with the elements necessary for life. The future of stellar nursery observations promises even more remarkable discoveries as new generations of telescopes come online. The James Webb Space Telescope, with its unprecedented infrared sensitivity and resolution, is already revealing the earliest stages of stellar and planetary formation with clarity that was unimaginable just decades ago. Ground-based, extremely large telescopes will soon provide optical and infrared observations with resolution rivaling that of space-based instruments, while next-generation radio arrays will map the molecular content of stellar nurseries with exquisite detail. These future observations will allow us to watch stellar birth in real time, following individual systems through their entire evolution, from first collapse to planetary system formation, creating a complete understanding of how stars and worlds are born from the gentle stirring of cosmic gas and dust in the vast, patient darkness between the stars. The eternal dance of cosmic creation. As we drift toward the gentle close of our journey through the stellar nurseries of the cosmos, let us allow our minds to settle into the profound peace that emerges from understanding our place within this vast, patient universe. We have traveled together through the dark molecular clouds, those cathedral-like structures of gas and dust that drift silently through space, carrying within their cold embrace the seeds of countless future stars. Feel yourself floating now in the serene darkness between the stars, surrounded by the invisible architecture of creation itself. The molecular clouds stretch around you like cosmic silk, their temperatures hovering just above absolute zero, their densities so ethereal that millions of cubic meters contain less matter than a single breath of Earth's atmosphere. Yet within this apparent emptiness lies the most profound creative force in the universe, gravity's patient, inexorable pull, gathering the scattered atoms of hydrogen and helium into the dense cores that will someday blaze as stars. Let your breathing slow and deepen as you contemplate the extraordinary timescales we have explored together. The collapse of a molecular cloud core unfolds over hundreds of thousands of years, each moment a whisper in the cosmic symphony of creation. The forces we have witnessed, gravity's gentle gathering, pressure's soft resistance, magnetic fields threading through space like invisible spider webs, all dance together in perfect, unhurried harmony. Picture yourself drifting through the Orion molecular cloud, that stellar nursery lying 1,500 light-years from Earth. Feel the profound stillness of this cosmic cradle, where temperatures of -260 degrees Celsius preserve the delicate molecular bonds that will someday fuel the nuclear fires of newborn stars. The dust grains around you, each no larger than particles of smoke, serve as the cosmic snowflakes upon which the first complex molecules condense, beginning the long, slow process of stellar birth. As your mind grows quieter, allow yourself to sink into the rhythm of cosmic creation itself. The shock waves from ancient supernovae ripple through space like gentle tsunamis, their energy dissipating over millions of years, yet still carrying enough force to disturb the delicate equilibrium of these stellar nurseries. These disturbances, spreading at the speed of sound through the rarefied gas, take thousands of years to traverse a single cloud. Their passage is gradual and inevitable as the changing of seasons. On a cosmic scale, feel the profound interconnectedness of all things as you rest in this space between creation and completion. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in the nuclear furnaces of stars that were born in nurseries just like these, billions of years ago. You are quite literally made of star stuff, your very existence a testament to the patient creativity of the universe itself. Let your awareness expand now to encompass the entire galaxy, that vast spiral of 400 billion stars, each one born from clouds of gas and dust, in processes identical to those we have explored. The Milky Way breathes with the rhythm of stellar birth and death, its spiral arms compressing molecular clouds in cosmic traffic jams that trigger new generations of star formation. This galactic heartbeat has pulsed for over 10 billion years and will continue for billions more, an eternal dance of creation that connects every atom in your body to the vast cosmic web of existence. As you surrender to sleep, carry with you the profound peace that comes from understanding your place in this magnificent cosmic story. You are not separate from the universe. You are the universe becoming conscious of itself, a temporary arrangement of stellar materials that has somehow developed the capacity for wonder, for love, for the deep contemplation of cosmic mysteries. Rest now in the gentle darkness of space, surrounded by the patient creativity of molecular clouds, knowing that somewhere in the vast expanse of the cosmos, new stars are being born at this very moment, their light destined to shine for billions of years, illuminating worlds we can barely imagine. Let this knowledge fill you with profound peace as you drift into the restorative darkness of sleep, your dreams carried on the cosmic winds that blow between the stars, in the eternal, patient dance of creation itself. Sleep well, cosmic traveler. The universe cradles you in its infinite embrace.